We'll start the session now. The topic will be model evaluation validation techniques. So for that, I warmly welcome Dr. Swati Jain, Associate Professor at Nirmal University. And briefly, I would introduce her that she is an highly respected academic and researcher with the background in machine learning, model evaluation, and advanced computational approaches. And she has contributed in reaching research publications and thousands of students. In today's section, she will discuss the critical concepts such as the performance metric, strategies, and practices for building the robust AI models. We will start the session now. And on behalf of GEC Modasa, I welcome you here today. So, session is yours now, madam. Wow, ma'am.
Am I audible?
Yes, madam.
Yes, ma'am.
Okay. So, good evening, everyone. And I was present in the earlier session partially, and I saw that the topic that was presented by Dr. Sharnil, I know him because he was an earlier colleague, right? So, I I was actually wondering that why am I given such a simple topic? But anyway, so this is a very simple topic that I'm asked to do, right? So I'll be sharing my screen. Give me a minute. Yeah, is my screen visible to everyone?
Yes, ma'am.
Yes, ma'am.
Yeah. So I'm given a very simple task of talking about the model evaluation and selection, right? And rather model performance matrix and model evaluation. This is the topic that is given to me. So first of all, what is a performance matrix? Let me make it small. Yeah. I hope my screen is visible and my voice is also audible to everyone. And I'll be talking about the performance metric in machine learning, right? First of all, and then we'll be talking about a little bit about evaluation and the performance metric based on the different type of applications. Okay. So performance metrics are quantitative measure used to evaluate the model's effectiveness in solving a task, right? There are different approaches like for classification. So there are different types of problems when we talk about machine learning or even deep learning. One of them is classification, where we are trying to put every instance into class. There we have accuracy, precision, recall, F1 score, ROC, and so on. Whenever we are talking about regression, we have mean absolute error, mean squared error, and R square score. And whenever we have clustering, we have the different score like Sellout score, Davis Bolden index, and so on. And the choice of the metric depends on the problem type. What is the problem that we are trying to solve, right? Yeah. I hope my screen is also changing when I'm changing the screen, and that change is visible to everyone. Now my screen reads model evaluation in machine learning, right? So model evaluation is the process of assessing how well a machine learning model generalizes to unseen data, right? So how accurate, reliable, and suitable it is. Now, how is the performance metric and model evaluation different? Because this example I always give, that it's not that you can run an algorithm once and you can say that, okay, I once run this algorithm and I got an accuracy of 95%, and I cannot claim the 95% accuracy. Rather, I have to give more statistically strong argument where I say that my model is 95% accurate because I have done enough validation with that. It could be a cross validation and many other approaches, right? So we'll be talking about more on that, right? So we are going to talk about the holdout method, the cross validation, and the bootstrap method in the model evaluation and selection strategies. And now for regression, if we talk about, the first is the evaluation metric for regression. So we all know what is a regression problem. I hope this topic is covered, the regression problem is covered. So when we talk about the regression problem, the output is a real number value, and we are interested in knowing that how close or away our predicted value is, right? So regression metric measures how well a model predicts a continuous value, right? They quantify the difference between the predicted output and the actual values. They identify accuracy and error in prediction, and you can use it to compare the different models and lower the errors and move towards the better model performance. Some of the evaluation metric is mean absolute error, mean squared error, root mean squared error, and R square score, right? So when we talk about, I hope everyone is aware of, just a minute. Yeah. So everyone is aware about the mean absolute error. It is the absolute value of your actual y minus y cap, right? Where it is the predicted value minus this and absolute value and the summation of it, summation of this value and over the total number of instances that we have, right? This is the mean absolute error. Now there is a difference, always there is a difference between the objective function and the evaluation metric, right? Sometimes people do confuse between the objective function and the evaluation metric. If somebody, I don't know how's the model we are studying. Am I audible and is my meeting already? Am I online? Because I can't see anything else on the screen.
Yes, ma'am. Screen is visible and you are clearly audible.
Okay, so can I ask questions in between, or it is better to continue with my session? How is the model that we are following? If somebody wants to answer, I will want somebody to volunteer to answer that. How is the objective function different than the evaluation metric? Okay, so the difference between the objectives, so sometimes we use mean squared error as the evaluation metric, and we also use the mean squared error as the objective function, right? How are they different? Objective function is the in between error tracking mechanism which we are going to use while learning, and use it as an important criteria to update our to update our attributes or our coefficients, right? The learning parameters. Whereas the evaluation metric is something that should make more sense to the end user, right? It is something that is used to for the user to interpret that how good or bad my performance is or the model is performing, right? So in the case of regression, we have the same mean squared error as the cost function or the objective function, which we are trying to minimize, and that is also the evaluation metric, right? But in case of classification, our cost function may not be same as our performance metric, right? So that difference we have to very clearly understand. Now, suppose mean squared error, right? If I say that, okay, my mean squared error is 325, right? Is 325.55, right? What meaning does it convey to you, right? Whether it is good, whether it is bad, right? That's a very like vague description of the amount of deviation from my actual answer, right? So the better measure of it is the normalized mean squared error, where whatever value we have, we normalize it between the scale. So 345.55 is my mean squared error, or suppose root mean squared error, to bring it back to the same scale. But then that 345 uh, is the error, mean error, uh, when the scale is 1000, 10,000, or when the scale is 100, right? If the scale is 100 and 200 and my mean square error, root mean squared error is in the scale of 300, then that is actually a very, very uh, big number, right? So the better measure for your evaluation metric, whenever we want to compare the two metric over different scale, we should always use a normalized or a normalized mean squared error, where the normalization is done for the sake of the scale that we are talking about, right? The other is the R square coefficient determination, right? How do we calculate that? R square coefficient is 1 minus SS, which is the residual sum of the square divided by the total sum of the squares. Now, how is residual sum and the total sum of the square or the variance different? Residual sum is the difference between the actual value and the predicted value, where y is the actual value and y cap is the predicted value. And the total sum is the squared, the deviation of the answer from its mean. So this is again something like normalization that we are doing, that we are normalizing our residual error with the variance, that how varied our values are, and dividing it by and 1 minus, that gives us the R square score, right? So that is the evaluation matrix for our regression problem, okay? Now, about the classification metric. The classification metric measures how well the model assigned input into predefined classes. So what happens, we have, let me select the pen. Yeah. So suppose the values are, the actual values are, which is y, is the class value 1, 2, 3, 1, 1, 2, 3, and your y cap values are 1, 2, 1, 3, 3, 2, 3, right? So how are we going to check that how good or bad it is? We compare the actual value and the predicted value. If they are same, we say that it's not an error. If it is not the same, then we count it as an error, and then we represent the error in a particular way, right? And accuracy usually is the most common way. Accuracy is usually the most common performance metric, but it is not enough all the time, right? Why it is not enough? Because especially in the case of imbalanced data, right? That one example that I always give is, suppose I'm a doctor, right? And I see, suppose 100 patient every day, and I'm a very, very positive doctor, and I ask whosoever the patient comes, and if suppose I'm an oncologist, and out of 100 patients, I see there are only 3 patients who are detected with that disease, right? The cancer, right? And the other 97 do not have. I'm a very optimistic doctor, and I say that you don't have any problem. That's good. That's good. That's good. That's good to all my 100 patients, right? What is my accuracy? Accuracy is 97% because I was right in the 97% of the time, right? But is that a good evaluation metric? No, it is not, because my job was to identify and not let go those 3 patients, right? And similar is the case of anomaly detection, when you or intrusion detection, when there are events which are not very common, they are very rare even, and those events are to be handled with caution, and your performance of your model should not just be evaluated based on metric, because 97, 98, 99 looks very fancy, but that 1% was its actual job, right? Which your model actually did not do, right? So the other ways of doing it, there are so many performance metric, like accuracy, error rate, sensitivity, specificity, precision, F1 score and F beta score, and we will see that how these values are important, right? Now there's a very important metric or very important evaluation metric, which is termed as confusion matrix, right? Now confusion matrix is a M cross M or cross C matrix. To make it simple, let us assume that our problem is a binary decision problem, and we have two classes, which is C1 and not C1, right? 1 and 0. So either it is C1 or not C1. And then we say that if this is our actual class, the row is the actual class, and so this row is this is our actual class, and the columns are our predicted class, right? So if the actual class was C1 and it also predicted C1, we call it true positive. If actual class was not C1 and it predicted not C1, it is true negative. Wonderful, right? But there are other errors where our actual class was C1, but it predicted not C1. The actual class was not C1, but it predicted C1, right? So these are the two types of errors, right? Now, often these terms, which is true positive, true negative, are very confusing terms, right? A key to it is that the first term, true, right, represents that whether the classification task has done its job correctly or not. So true and true, right? It means that the classification, whatever was the initial class, the classification is done correctly. So it is either true positive or true negative. True positive, the second term represents that what it has predicted, right? So when you say true and then you say positive, it means it has done its classification task correctly, and the class is positive. The output class is positive. Whereas in this case, the classification is done correctly and the output class is negative, right? So when the moment you listen true, it means the classification is correct, right? That is assured. Now, there are two types of misclassifications. One is false positive and false negative. The moment we listen false, we know that the classification task is incorrect. And positive means it is incorrect and it has resulted into a positive class where the actual class was actually negative, right? So the second term says that what is the prediction? The prediction is positive, and in this case, the prediction is negative. The actual class was C1. But it's not the case that the classification or the this matrix confusion matrix will be only of two class or binary class. It can be of multiple classes. For example, we can also have C1, C2, C3, C4. Suppose there are four classes, and then we can have C1, C2, C3, C4. All the diagonal elements would be representing the true classification. C1 classified as C1, C2 classified as C2, C3 classified as C3, and C4 classified as C4. And all other values other than the diagonal elements are termed as a misclassification, meaning that C2 classified as C1 is a misclassification, C3 classified as C1 is a misclassification. So whenever we have to find out the accuracy, if you add up the diagonal elements, we know these are the number of the correct predictions divided by the total number of the instances. That gives us the accuracy. A very simple rule, right? I am sure everyone knows about it, right? Now, in this example, suppose Bai's computer, there are total 10,000 instances, right? And we have 7,000 that belongs to yes, right? 7,000 that belongs to yes, and 3,000 that belongs to no class. Out of that, 7,6954 is identified as yes, and 2588 is identified as no, which is the correct classification. Whereas there are 412 plus 46 misclassifications, and something which was actually no and is classified as yes, and so on, right? So if I add up the rows, I get the total number of, right? So if you talk about the number 46, right? If you talk about the number 46, this is actually yes, but classified as no. So if at all I want to find out how many actually yes classes was there, I'll have to add up these rows, right? So summation of rows, no matter what is the dimension of our confusion matrix, will always tell us the total number of the instances that were actually belonging to that class, and the summation of the columns will always reflect like 7366. It means total uh, uh, the total number of classes 7366 is the instances which were actually classified as um, yes, and so on, right? So this is the brief of the confusion matrix, and we often use true positive, true negative, false positive, and false negative to specify the other terms or define the other terms as we have done it here. So when we say true positive plus true negative, it means the summation of all the correct prediction divided by the total number of instances. When we are talking about the error rate, it is the total misclassification. So false classification as positive and false classification as negative divided by the total, right? Now, there is something which is known as sensitivity or recall, which are the same thing, right? Sensitivity and recall. Now, sensitivity, recall, or true positive rate. So, total number of true positive, how many were actually positive, which were classified as true positive, right? That is what is known as recall or sensitivity, right? Then specificity is true negative divided by the total number of negative, that is specificity, which is true negative rate, right? Now precision is that out of total. Now if you see the denominator, it is true positive plus false positive, means the total number of instances which were classified as positive, but how many of them are correctly classified as true positive, right? Now, precision and recall are a little tricky. We'll discuss about it and we'll talk about these scores in our next slide. Right, so we already discussed about it. We discussed about error rate, we discussed about sensitivity, we discussed about specificity and so on, right? Now, precision and recall. So when you have a multi-class scenario, when you have 4 or 5 multi-class scenario, then we find out the precision and recall class-wise, okay? Precision and recall class-wise. How do we find out precision and recall class-wise? So if I have to find out the precision, we say, so for example, we have to find out the precision of class 1, right? So how many instances are totally correctly classified as class 1 divided by the total number of instances which are classified as class 1, whether correct or incorrect. That is what is known as true positive divided by true positive plus false positive. But whenever you have multiple classification, right, multiple class classification, in that case, there is nothing like true positive or false positive. Okay. For example, in this case, the matrix that we were trying to say, if I have to find out the the precision of C1, then I'll say that this value divided by the summation of this column, right? Because these are the total classification as C1, whether they were belonging to C2, whether they were belonging to C3, or whether they were belonging to C4. So there's no point trying to memorize. There's no point trying to memorize. Is there any question? Because I can't see the screen. I only see, but I hear some beep. It means somebody is raising hand or somebody wants to ask something. If you want to ask something, please feel free to unmute and ask. Otherwise, I am not able to see the other screen where somebody is raising hand or somebody is trying to write something on the chat window. Okay. So precision is the total precision class-wise. So usually the output that we receive is precision class-wise, that all the instances which are classified as C1, out of that, how many are correctly classified, as C1. Precision of C2 means out of total instances which are classified as C2, how many of them are actually C2, and so on, right? Now, there's something which is known as recall. Recall is that out of the total positive, how many of them are classified as positive. Now, precision and recall are like related to each other, right? The numerator is the same, but the denominator is different, right? So true positive means something which is classified as class C. Now, suppose I am trying to search, suppose I am trying to, in my database, I have 200 images of aeroplane, right? I'm trying to search the aeroplane. I give my query as aeroplane, and it picks up, suppose 20 images, right? Out of that 20 images, there are 15 images which are aeroplane and 5 images are not aeroplane. So my precision is out of 20, 15 divided by the total number of images which are classified as positive. So which is out of 20. So that is my precision, right? What is my recall? Out of 100, it only picked up 15, which was aeroplane. So it is 15 divided by 100. The moment I increase the number of images which I'm going to pick up, my recall goes up and my precision goes down, right? Recall goes up and my precision goes down. So there has to be a good trade-off while we are choosing the precision and recall, especially when we are using these terms in case of in case of uh, retrieving information retrieval, right? Then we talk about F1 and F score, which is the harmonic mean of the precision and recall. We can also calculate the precision and recall for different number of values, as in case of the retrieval, and we can talk about that F score. And this is the weighted measure of the precision and recall, where we assign different weightages to the precision and to the recall. Depending upon the value of the beta, the precision is more important, recall is more important. We can take a call and accordingly we can use that values. This is one example that I am assuming that not required at this point of time, right? This is one example of calculation which I can leave for now. Okay. Now, the other important parameter is top 1 and top 5 error, right? Now, in this scenario of machine learning, and especially when we are using artificial neural network a lot, right? And whenever you have not just 2 classes but multiple classes, right? So, if suppose I talk about the deep learning models like AlexNet, or if I'm talking about deep learning models like GoogleNet, right? All these models are trying to classify the database, which has got thousands of classes, right? And then what we have in the output layer, of the neuron, so in the output layer of the neuron, we have the number of neurons, which is equal to the number of classes. Okay. So suppose I had 6 classes, then I'll have 6 neurons in the output layer. And the output, when I say predict, right, and I give the model and I give the input, right, what happens? I will get a vector of 6 values, right? A vector of 6 values. And I'm going to, how am I going to interpret it? I'll find out the argmax of this, and I'll find out the index where my maximum value is there, right? So suppose the maximum value, in this case, for example, Cherry gave the value 0.35, Raspberry gave 0.24, and so on. And the highest value is Cherry. So if my actual answer was Cherry and the maximum value has made it to Cherry, then I'll consider it as correct, which is known as top 1 accuracy, right? But whenever we are talking about multi-class classification, especially in hundreds, we say that there are other parameters that makes a lot of sense, right? So suppose cherry had the value 0.35, right? Cherry had the value 0.35, and Raspberry Pi had the value 0.25, right? This value and this value, right? 25. Now, suppose I have to, this value 0.25 instead was 0.34, which was very close, right? And my actual answer was Raspberry. They were very close, very, very close to each other, but it is only that it did not make it to the position 1. So what we look for is that if my actual class value makes it to one of the 5 top positions, then I do not count it as error, right? So what is top 5 error? Top 5 error is counted as error if my actual class do not make it to top 5 of the predicted vector, right? Predicted vector values, right? If my actual class do not make it to the top 5 position, then only I count it as an error, right? So if at all it is able to make it to first, second, third, or fourth, then we count it as not an error, right? So that is known as top 5 error. And often if you see any paper, they are actually claiming, they are actually reporting not just the accuracy, but especially in the case of classification and multi-class classification, top 1 error, top 2 error, top 3 error, and top 5 error. These are the 3 important criteria that everyone is using to demonstrate the value, right? Now, the other thing which is termed as the ROC curve, right? Now, what is ROC curve? ROC curve says that if at all, right, what does it evaluate? It evaluates the learnability of my model, right? Learnability of my model. Learnability means what? That if at all my model has actually learned the concept clearly, then there must be then this probability value, which I am seeing in the third column, right? The probability value should show some pattern, right? Now probability means what? That all the positive classes should have the higher probabilities, and all the negative class should have the lower probability. And therefore, as I keep on increasing the decreasing my cutoff rate, then my true positive rate and false positive rate should show some pattern, right? Should show some pattern. Now, how do we see that? So what we do is, we first of all, because this is an important concept which is also used when we are talking about image localization, okay, and we will see that how the same probability concept or cutoff concept is going to help us evaluate that whether our model has actually some pattern in the positive classes and the negative classes or not, right? So when we talk about the probability means, especially in the case of neural network, where our output is the probability value, and then we say that, okay, this probability value greater than 0.5 is yes and less than 0.5 is no, and so on, right? So accordingly, we are trying to say that how this probability values, when made as a cutoff, can change can give us a perception of whether our system has learned or not, right? So what we say is that if our class is positive, and we say that anything which is having a probability of 0.9 will only be classified as true, otherwise everything will be classified as false, right? So in that case, the moment I say my cutoff is 0.9, this is the actual class, my predicted class becomes positive, and the all other becomes negative. All other becomes negative, right? Everything else becomes negative. This is the prediction that my system will be giving. And because of that, my true positive is 1. There is no other positive, so false positive is 0. Now, how many true negatives? True negatives is 1, 2, 3, 4, and 5. There are 5 true negatives, and there are 4 false negative, which were actually positive but are classified as negative, right? So, and then I reduce my cutoff to 0.80, right? And then I say everything else is negative except these two, right? So my true positive is 2, and accordingly the values have changed, and I'll find out the true positive rate and the false positive rate, right? And I keep on decreasing my cutoff to the lowest value, 0.4, and accordingly I get the 5 as a top positive, 5 is a false positive, and that is how my values would change. And finally, when we plot it, when we plot the values, which is like this, when the first cutoff, when the second cutoff, when the third cutoff, fourth cutoff, and so on, when we plot it, then we say that if at all, it is a straight like this, it is a total random guessing. It means your model has learned nothing. It is just doing a random guessing, and there is going to be no change in your performance, no matter what is your probability cutoff, right? Then we say that if at all your area under curve is above your random guessing, then there is some learnability, right? We find out the area under curve, and if the area under curve is close to 1, we say that okay, the learnability of the system is very high, and if it is below it, it means doesn't make any sense at all. Random is the worst behavior, right? So if the ROC curve is above, more far off from the 45 degrees, the better it is, right? This is how we talk about the ROC curve. Okay, now suppose the problem definition has changed, right? The problem definition has changed. And what is the problem definition? The problem definition is object detection, right? Now, so far, what was my problem definition? My problem definition was that if I give a value, then in case of regression, I give my attribute A1 to attribute AN, and then I get a value Y, and I will find out which is a real number. So it was important that how close or far the answer is. Therefore, the performance metric was mean squared error and so on, right? Mean squared error, root mean squared error, and so on, right? The moment the problem definition changed to classification, right? My attributes are A1 to AN, or it could also be image, and the output is the class value, right? So the class value is 3, 2, 4, 7, and so on, right? Now, if my actual class was 2, 4, and 7, this is a misclassification. No matter it is classified, 3 is classified as 2, or rather 2 is classified as 3, or 2 is classified as 7. Wrong is wrong. So there, subtracting and mean squared error does not make any difference because they are not ordinal in nature and they are not numbers, right? So it does not make any sense, okay? So therefore, the performance metrics are different, and we said that the performance metrics are accuracy, where we only compare, we do not find out the difference between the two. I mean, we do not subtract the one value from the other value, okay? Then we count, it is based on the counts of the total number of correct prediction and the not correct prediction. The other problem that comes is known as object detection, where the task is not to give image as an input and give the class value car. Rather, it is give image as an input and give the bounding box, right? Give the bounding box, and that bounding box defines that what is the object in it. So there are two outcomes. What are the outcomes? one of the outcome is this box, right? One of the outcome is this box, right? This box, and the other is the class value of the box. Now this box is how correctly it is placed. So suppose my algorithm is predicting this as the as car, right? This as car, right? This is not wrong, right? This is not wrong, but this is also not very correct because it is unnecessarily covering the area which is not the actual answer. So there is something which is known as intersection over union, right? Intersection over union. This parameter is also very important whenever we are talking about this the segmentation as the problem. Not getting into that, so we'll try to see that how close are these predicted values, right? So we will have to define some performance metric that can evaluate or quantify that my localization problem, which I had defined, which requires two types of output. One is the class value and other is the location of that or the bounding box inside it, right? So how good that bounding box is, and I need a quantitative measure for the same. Okay, right. So the term intersection over union is defined as the size of the, so for example, there are two boxes, green and yellow, and we have to find out that what is the intersection over union. So it is the total area, right? The total area, the entire union, which is the green area, and the intersection, what is the common areas between the two, right? So the actual answer was this, and this is what the system predicted, right? This was the only area which was correct, right? So what was the total otherwise wasteful area, which is either incorrectly added or incorrectly left, right? Which is the green area, which is the intersection of the two, and what is the intersection of the two, and what is the union of the two. We take the ratio and we say that what is the IOU, right? Intersection over union. Okay. IOU is a measure of overlap between the two bounding boxes, as I've already mentioned it. Okay. Now, how is my output going to look like? The output is going to look like not just one value or the class value, rather the class value and the bounding box value, where I say that this is the bounding box, this is the BX, this is BY, this is BH, and this is, so X and Y is the center of the bounding box, and H and W is the height and width of the bounding box. Okay. Now, the performance matrix which is defined as mean average precision, right? MAP, right? MAP, mean average precision. So we say true positive, a correct detection. So it is the detection with IOU greater than or equal to threshold. So we say which is a correct detection is true positive as always. False positive is a wrong detection, right? A detection with IOU less than threshold. It means that my bad. Is somebody asking a question? Is somebody asking a question? Okay. So, yes, Meenal Chauhan is saying something, I suppose. Can you unmute yourself and ask?
No, ma'am.
Meenal
I guess I'm joined. I'm joined from another device, so by mistake. Sorry, ma'am.
No problem. Yeah. So, false positive, a wrong detection. So, something is detected, but the IOU is less than the threshold will be considered as a false positive. And false negative, a ground truth, but which is not detected. So, we already have a ground truth which is not detected. So, now how are we going to do it? So, let us look into this, right? Where what we can say is that we already talked about the true positive, positive, false negative, right? We need to calculate the precision or of each of the recall, and then we average the precision over all these recall, and therefore we say it is the average precision. Okay. Now, how are we going to mean average precision? How are we going to calculate that, right? So, for example, in case of this one, um, true positive or false positive. So, in case of A, right, even if the confidence is 88 percentage, we say it is false positive, right? So, when we are saying this value, this value, right, in this case,
Hello. Hello, madam. We cannot hear you. Hello. Hello. Hello.
Let's just wait a minute. I think due to some connection problem, madam has left the meeting. Just wait for 2 minutes. Hello. Okay. It seems that ma'am has disconnected and we are not able to contact ma'am. So anyway, the time is almost up. So today's session we will end here. And even if ma'am is not here, but I would like to thank her for the wonderful session. And for participants, we are very sorry for such kind of trouble. And